¿Quién lo tiene entonces? Dímelo todo. ¿Eres tú?
Ahí está, vale, entonces basta pararlo y volverlo a poner esto.
Como diría Mateo. Guapa, guapa.
Va.
Vale, pues perfecto. ¿Ya estamos solventes? Sí. ¿Nos da tiempo a...? Sí, yo creo que sí. Perfecto. Hoy. Bueno, claro, es verdad.
¿Cómo?
Traes una... Bueno, ahora sí no nos traemos a la vuelta. Sí, no, claro. Vamos a hacer un poco de ejercicio pulmón. Yo sí me vi un vídeo de...
Hi. Hey,
Ay,
can you hear us well? Yeah, we hear you.
bien. Uy.
Deberíamos bajar.
Stop.
Jak tam współpraca z rynkiem polskim?
Fajnie, teraz chcemy bursty i jak się pamiętam inne regulatorem mają jakiś artykuł Integrated Manifolds albo Windows, coś takiego. I chcemy teraz robić jeszcze raz, ale z innej perspektywy, bo to jest shifts i tak dalej.
Myślę, że oni tak zrobili z tej perspektywy właśnie tych shiftów. Okay.
I teraz chcemy jak klasyczna geometria, układ współrzędny.
Okay. Wtedy opublikowaliście już ten artykuł o...
Jest na archive.
Tak, to widziałem, że jest na archive. A wysłaliście go już gdzieś?
Tak.
Na
Raksam jest gazeta Hiszpańskiej Akademii Nauk.
Jeszcze raz jak się nazywa?
Revista de la Real Academia de Ciencias y
Okay.
el Tribunal de la Real Academia
Co Natalii słychać?
Dobrze. Ożeni się.
Jeszcze raz?
Ożeni się.
To będziecie się żenić. Mam to gratulacje.
Dziękuję.
Kiedy?
21 lipca.
Okej. Będzie ślub cywilny, tak?
Tak.
Okej. No to gratulacje.
Dzięki.
Co planujecie? Jakieś wesele?
Tak. Tutaj będę malutkie, a potem zrobimy imprezę we Hiszpanii.
Okej. W Madrycie?
Blisko. Segovia to jest inna prowincja.
Okej.
Hello.
Jak się czujesz?
Dobrze. Faktycznie ja żyję jak żonaty dawno temu, ale... Okay, maybe do you want to start or are we waiting for...
No, we are all here, I think.
No más, ¿no? ¿Qué no cierra? Por eso porque tiene mucho espacio.
One sec. We are having coffee problems.
Coffee?
Coffee problems, yeah.
I see. Okay, now it's when I try the camera.
Wait, it's moving.
Claro.
Do you record?
Wait, let me check.
To seems like the elections.
Yeah, whenever you want.
Bueno, igual, ¿no?
Maybe disconnect the camera?
Ah, sorry, yes.
Yeah, no problem. Okay, welcome everybody once again to the meeting point. And today we have the pleasure to host Bartosz Zawora, who will talk about symplectic coordinations.
Thank you very much. Yes, so today I would like to tell you about the first most symplectic groupoid actions. First, I'll show you and define the groupoid action. Then we move to the symplectic setting. I will comment on some, as you expect, the symplectic groupoid action is a generalization of a symplectic action of a Lie group on a symplectic manifold. So in particular, this generalization will lead to general theory of Hamiltonian reductions, generalization of Weinstein theorem. And then I will also comment on the non-Hausdorff Lie groupoids. Yeah, so this is more or less the plan for today. So first, let me tell you what is the action of a Lie groupoid. So let me start with the definition. And so that the Lie groupoid and let the amount from S from S to M, where S is some manifold. Okay, now the action of a Lie groupoid on Emma mu this first of all Emma. It's polygraphic A, the smooth map G from G S to S, where this is defined as first G in G times S, such that the in this case source of G is equal mu phi. Okay. Yeah, so this smooth map from G times S to S, such that first of all mu of G sometimes a notational thing is that sometimes ATP will be denoted by G times P. But I will try to remember it using the same. Okay, such that mu of ATP equals target of G. And we have, like, let us say, standard conditions, which is the identity mu of P is equal to P, and G HP is equal to GHP. Okay, so now I'm not using the same because I mean it's understandable. So of course, if a groupoid, okay, so this naturally generalizes the concept of a Lie group action, and let me show you some examples, or maybe one example, which is the gauge groupoid. Okay, just let me also draw a picture, which somehow diagram maybe would somehow visualize the reduction. So usually it's denoted as you have a groupoid acting on S, we have mu, and we have an groupoid over L, right? So this is the diagram illustrating the definition of a groupoid action. Okay. Yes, for example. Gauge groupoid.
Guys,
So, yeah.
the camera has gone a bit astray. Okay, maybe it's fixed now. Okay, we see now.
Isn't it like too far?
No, now I think it's okay.
No, it's okay.
So here's diagram illustrating the Lie groupoid action, and now I will show you an example of a Lie groupoid action on a gauge groupoid. Okay, so first of all, well, we have some G over M, right? And the elements here are the equivalence classes of pairs U1. Denote this as this. And let me just recall you just the target. The target of this is the projection of U2, and source of U1 is the projection of U1. Okay, so what is the action? So I will show you the action action A along the map mu, which is just the projection from the passage from the points. Okay, so this action yeah, this action is first of all the takes the element of a cage groupoid, which is U2 U1. It takes the element of P, right? So U, but remember that what I mean, it cannot be like every U, but in this case, the source of G must be equal mu of P. Okay, so U is our element of P, but mu is just a projection, and the source of G is projection of U1. So here it's just U1. Okay, and this action is it gives U2. And indeed this condition, which is target of G, is the projection of U2, and the mu, which is just the projection of this, which is just U2, is the projection of. So it's indeed a needlepoint action. Okay. So this is an example. I show another example in case of symplectic setting, which will be in a moment. Okay. Definition. Let sigma omega over M be a symplectic groupoid be a symplectic groupoid and let her as omega be a symplectic manifold. Yes, those. The groupoid action from G times F equal to S. But here I said on mu on mu from S to M is symplectic groupoid action as a symplectic groupoid action if the pullback of omega, the small omega pullback from S to G times M is equal to the pullback of capital omega with respect to the first projection plus the pullback of small omega with respect to the second projection. Okay, where so as sorry, here I said this to be projection 1 says so sequence and projection 2 says yeah, of course. Okay. So yeah, so this is the definition of a symplectic equipoid action. Okay. Do you have any questions so far? I mean, it's not nothing complicated, but
The map mu, generally the definition of equipoid action, it just has to be a smooth map.
yeah. In a general setting, yes. In the case of in the case of reduction, you will take the. I mean, it's in the case of like the standard symplectic reduction, this will be a momentum map. So you like want to require from you that the level set of this submanifold, so then you need to add more condition. But in principle, it's just a small map from S. Okay. So here is this. Okay, and let me show you another example. Just quickly recall that we recall you that and of course you will remember that a symplectic groupoid, and it's a groupoid with a symplectic form that is multiplicative. Okay, so yeah, let's consider the following example. So let sigma omega be a symplectic groupoid, and action the action is from sigma times that's okay, yeah, times sigma. So sigma action on target map. Sigma. And it's a trivial example, but okay. So I mean, it's indeed the action, since I mean this multiplication here, this action is just the multiplication, the algebraic, sorry, and this is just the set of composable arrows. So the source of the left must be equal to the target of the right, and mu, and of course this is the composition. So the target of G is equal to the target of the composition right of G H, which is mu of G H, the target of G H, and this map must be above target of G. Of course, specified because this is composable arcs. Okay, so why it's the symplectic equipoid action? Well, what is this? I mean, since the action in this case is just a left equipoid action, so it's only the product of omega with respect to the multiplication map, and this is what sorted. So this is the example of a symplectic equifunction. Okay.
And I guess it's very natural to generalize this definition to just instead of symplectic groupoid and symplectic manifold, you just have groupoid endowed with a K form and another manifold endowed with a K form such that they are related in a multiplicative.
Yeah, exactly. And this is the usual. This is the usual thing where people they could prove the reductions for using this groupoid set for different geometric structures. So that's I'm aware of co-symplectic reductions. I'm symplectic, of course, co-symplectic. There is a very nice paper about the contact also groupoid actions and reductions. And yes, I mean indeed it gives more general results, but at the end, it, doing the reduction, performing the reduction, you need to compute the kernel of a symplectic form and so on. But of course, as we'll see, we can get much more general results. Okay. So yes. So we have I showed you or defined the lead action of a groupoid. So we of course also have the infinitesimal version, which is an action of a Lie algebroid. Of a Lie algebroid. Which is denoted by a it's a algebroid A over M on amount S M is a Lie algebra homomorphism just and it's from the sections of the algebroid, the vector fields on S of such that this is natural, which is the C infinity and linear, which says that alpha of F times alpha, A of F times alpha. But in this case, you want to vector fields and next, so we have to take a full part of the function F A on alpha. Okay, and the second thing is that it needs to be compatible with non-formal. Careful from M, which means that Okay. So how we can starting from legal point action, we can get an action of a Lie algebroid. Let me show you how it is done. Work with legal point action on S along or on S adjacent. Right, and we can construct the induced action of the algebroid. So
Sorry.
this
The camera is.
yes, sorry.
No, it's.
We have changed the settings.
Could you maybe, Bartosz, please go again on the compatibility with the anchor?
Yeah, sure. Yeah, so the second condition is that we establishes the compatibility with the anchor of the Lie algebroid, which basically means that if we take the section of Lie algebroid and then we act on by this action of the Lie algebroid, right? So this is an element um, it's a vector field on S. Then we have to apply tangent map TP mu, which gives us an element on TS. Right, but this is the same mistake if this is the anchor of alpha at point mu of P.
Yeah. Okay, thank you.
I mean, it's somehow natural condition. Like, okay. Okay. So how to construct the associated Lie algebroid action with the Lie groupoid action, I mean action of Lie groupoid, sorry, on mu. Well, I mean, of course, the Lie algebroid will be just Lie of G. And this will be the action of A on mu S times sorry, mu S O M from S to M. And for P in S and mu of P in M, we construct the following RP. It's a map, I mean, it's a map from machine, it just takes an element. But it's not every G, we take G in a G fiber of X. And like just G fiber and P, and it gives us the element in S, G minus 1, G minus 1, and this is easy. And then the action of Lie algebroid is just taking the tangent map. So the A at P is defined as the tangent map at unit at u of X RP, right? And by definition, it acts from a Lie algebroid at X to the TPS, tangent space at best. Okay. So we know how to construct the Lie algebraic reduction or Lie algebraic from the action of the Lie groupoid. So now going back to our symplectic setting, the general idea is to generalize the classical symplectic like Lie groupoid Lie group setting. So instead of action of a Lie group, a symplectic group of actions, we want to consider the symplectic Lie groupoid action of a symplectic Lie groupoid. Instead of momentum map, we want to have the general view, right? So instead of dual Lie algebra, we want to general symplectic manifold. So the idea is to replace G stars by general Poisson manifold. Momentum maps by Poisson maps. And Hamiltonian ego functions by symplectic groupoid actions. Okay. So this is the idea. So before, okay, maybe we, how much time do you have?
Like an hour, I would say,
Okay.
or 55 minutes.
Okay, so let me recall some notation. I think I think it was Manolo or Oscar who was talking about the symplectic groupoids. I'm not sure, but let me just recall you that we have a canonical Lie algebraic isomorphism, which is denoted as sigma omega, and it's from Lie algebraic over Lie groupoid sigma, symplectic Lie groupoid, and E star goes to E star m, such that it takes alpha and maps to minus a unity map and the pullback of the contraction out of omega, and we take the pullback of the unity. Okay. Yeah, so this is the Lie algebraic isomorphism. Okay, so this will be useful in a moment. Yeah, I'm sorry, and in particular we have that P hash, which is the induced vector bundle isomorphism induced by Poisson structure. It's usual, and this is given by rho composed with sigma minus 1 omega. Oh, okay, but maybe I didn't say try correctly. But, just to be sure, we start from symplectic group body and pi is the Poisson manifold. So this is our take. Okay. So now let me move to the proposition I want to show you, which is let me say a crucial proposition for reduction theories in a setting of symplectic mean group bodies. So first of all, let sigma omega e over n I be a symplectic yeah symplectic group body with an associated Poisson structure. Then for a specific symplectic group body action. On from S, yeah, from S to M, where S only gets symplectic. One S the following. So first of all, you move from the right in this way to M I is a complete Poisson map. And the second is that the induced the ulterior action satisfies the fullback of mu and the fullback of sigma omega of alpha with respect to mu is the contraction of A alpha with the symplectic form on S, which is omega. So this is the proposition. And yeah, keep in mind that the first the first statement says that mu is a complete Poisson map. So it's just a remark that in here we consider legal points in the sense that, of course, smooth structure and so on, but also that the manifolds are Hausdorff. In the non-Hausdorff setting, which I will comment later, but in a Hausdorff setting, of course, you will have problems with the existence of clauses of the vector fields and with completeness of vector fields and so on. But surprisingly, even in not completely, in a frame that will not allow non-Hausdorff manifolds everywhere, but even if we lose this condition that some manifolds will be non-Hausdorff, not everyone, not every manifold. We will still be able to recover most of the results. Most of the results they present today. And actually even more, but I will comment on that later. Okay, so let me show you the proof of this proposition.
I'm sorry, Bartosz, if you said it already, but can you? I don't quite know what complete means, like on a Poisson map.
Yeah, sorry, once again, could you repeat?
Yeah, what does it mean for a Poisson map to be complete?
Complete Poisson map. Okay, let me recall you. I mean, okay. What Poisson means, it's understandable.
Yes, that part.
Complete. So let me recall the definition that adds to M. And is complete. I mean, it's but do you remember the symplectic realization? What does it symplectic realization? What does it mean? What means the complete realization?
Yeah, for like compact Hamiltonian vector fields or to be complete.
Yeah,
no?
so it's the same.
Okay.
It's complete if for any Hamiltonian vector field on M the Hamiltonian vector field X H composed here is complete.
Great, thanks.
You're welcome. Okay, so let me proceed to proof. So let me start with the second state. So let me rewrite it that we want to prove that sorry, sigma omega false positive is equal to construction with okay. Yes, maybe let me draw the diagram just as well. Yeah, the diagram will be as follows. These are S. S. This is the dual tangent material. Here we need a toroid. It's sigma omega. We have since it is symplectic, so the chart, associated with omega. Sorry, I'm sorry. Mu is from S to M, so it's M, and here we have the Poisson structure. All this, so it's from this for M. Here we have an anchor. In here we have a P sharp associated with no wait. I'm sorry. Here is R, it's dual map. Sorry, it's dual map. P sharp, of course, is like the element of the dual, and it gives us an element of tangent space, and the same in here. So it's DPS, right? And here is so now what we need to show basically in the second statement is that this upper triangle is commutative. Okay, so let me just write what is sigma. Sorry, what is this? Well, it's sigma omega of alpha is okay. Erase this. Well, sigma equals mu minus over confusing the alpha of omega. Okay, so we can this condition can be written as follows. So we take minus u, sorry, minus u means that the full box. And here we take omega on first of all the anchor is not anchor, it's or section of a of the algebraic. Then so we just get rid of mu's part, but we put it in here. So it's dp of an vector p, right? This is fx, and sorry, is this, and this equals omega of a of alpha on v, where v is an element of a function space of S. X is mu of t and n. Okay, so we just take this. We take this formula on a vector field on a vector field V. This is one form on a manifold S. So we just take the vector tangent of this manifold. Okay, so now we will use the construction of the action of the algebroid. So what is, first of all, we want what is AT on alpha? Well, it's just the tangent that's unit x, unit of x, and p, the action of, first of all, we have a tangent map of unit x of yeah, because this action, like it was by construction from a E group point action, we had like g to minus 1 E, right? So since by construction is g to minus 1 of P, here we have tangent map to a inversion. Inverse map of alpha, and here is the zero vector. So this is the first thing, and moreover, since A of u of x times p is just p, so if we take a curve on S and then we compute the derivative with respect to t and so on, we get as a vector field v, which is some t0 over the curve, the tangent, and the tangent vector. The v is tangent vector to a derivative of curve at some point of 0. The thing is that the tangent function that u of x t a is the so t of u mu of alpha. Sorry, not alpha, but v, and here we just get v. Right, and this is for every vector in this. So this is our setting. So now we want to use that we have a symplectic group reduction. So first of all, note that in here we have a zero vector. And so what we get from the definition, by the definition of a symplectic group reduction, we get omega at t of a alpha b is equal to omega u of x, the unity of x, on t u of x, the inverse of the tangent map to the inverse at unity of alpha, with the first argument. The second argument is that this is the tangent map at p to u of t of p. Okay. So let me erase the first some part of the first blackboard. yeah, so we have this. So now we'll use two properties. First of all is that the fullback of omega with respect to the inverse map is just minus omega. I think it was short about during the lecture on symplectic properties. And the second thing is that there's just right, because the idea is that yeah, here we have an inverse map, so we can take a pullback. The inverse map is inverse to itself, so we can take a pullback of the inverse in here. Then we get here the composition of the inverse with the unit, which is just the unit. So we get like this. We get that on the left, which is a alpha e, right? Because here is exactly, no, sorry. Yeah, here. So this part is exactly this part. So this is the part that we want to show that equals this. So in here we have a minus by this. So we get this is minus omega u of x on alpha, right? Because we get rid of this inverse alpha, and here we get this is the tangent, and we uniform pose to yeah, but this is exactly the definition of a sigma of omega. Right, so the first part this proves well, it's the second part. Okay. Do you have any questions? If not, let me show you the proof first part of the position. So now we want to show that that the map U is first is a Poisson map. Yeah. So yeah, proof. U was the second on the first statement. Okay. Here is this Poisson. Okay, so what one needs to show, I'm using this diagram, B mu Poisson basically means that B hash is equal from the maybe from the back. So it's P star mu composed with P hash omega composed with E. So we need to show this. But this follows if this diagram is continuity, right? So this is commutative by the second statement. Basically, this is what we showed. So this is commutative. This is what? Okay, yeah, this is commutative because the sigma of omega is a Lie algebra isomorphism, and this is commutative by definition. Yes, sorry, because here we have p. So this is commutative since sigma omega is a Lie algebra isomorphism, and this is commutative by definition of an actionable Lie algebra action. So this diagram is commutative, so the result follows. I mean, which can compute the hash omega if you start composed with sigma omega. So what is this? Well, we take an element b from here, we are here, then acting by this starting we are here, p hash associated omega we are here, and then we are here. So this is the same as we take the action. So it's t. Use without this tangent on the middle, composed with an actionable algebraic. But this, by commutativity of this diagram, is just wrong. And wrong, as I recalled you in a proposition presented a couple lectures ago, like it would be just recall once again that sigma yeah. Let me write it first. It's raw, and raw is it's the okay. Once again, raw is p. I mean the first sigma of omega and then p hash. By commutativity of this diagram, so sigma omega, so we get that mu indeed is a Poisson up. Okay. So now we show that it is complete. So let me erase this line. Yeah, show completeness. So to show completeness, assume that one vector field is complete. Okay. Yeah, let's first in H is the function of n, and so the vector field. So we need to show that X H composed is complete. This is what we need to show. Okay, so let's let us denote by alpha sigma omega minus 1 of the dh. Okay, so we take dh in here, and we take sigma omega to minus 1, and this gives us this element, and get the section of a algebra. Okay. So note that first of all, each stage can be written as follows. So this is vector field, the vector field on M. So this is written as the d hat of dh, right? But this, using the commutative part diagram, we can write it as the anchor of sigma omega minus 1 of dh, which is the anchor of alpha. Okay, so the second thing that we observe is that how we can write the vector field, this vector field on an S. Well, it's a d hash of omega, since it's the Hamiltonian vector field on S. It's d hash d h composed with mu, and composed with mu. But this is, this is the pullback of h, pullback commutes with the differential, so it's d hash omega d star mu of dh. And again, by the commutativity, we get that this is exactly a of sigma omega minus 1 of dh, which is a of alpha. Okay, so XH is complete vector field, which means that rho of alpha is complete. But rho alpha is a complete. This means that alpha is a complete section of the algebraic. So since alpha is a complete section of the algebraic, we use the Polish proposition, which says, I think, I'm not sure, but I think Asir presented it during your lecture, that if alpha, the section or the algebraic, is a complete section, then the left invariant vector field on on sigma in this case is complete. Okay, so here we show that alpha is a complete section of any algebraic entity. So using this proposition, we conclude that the left invariant vector field is complete. Okay, so what is left, since we show that alpha is a complete vector field, what is left to show that the flow, we need to somehow show that the flow of this, which is just A of alpha, is somehow related to the flow of the left invariant vector field. But well, it's just a matter of observation that the flow of A of alpha at E. So this flow is given by the following flow. It's the ligatory action of the flow E of left invariant vector field alpha at mu of E on this is -1 on C. Okay, so indeed one can, I mean, it's just a matter of differentiation. Once it gets that this is mu is A of alpha is complete. Okay. Yeah, this is complete because the part on the right hand side is complete. Okay. So we prove the proposition. So hope it was understandable. I have 15 minutes. Yeah, so I will not tell you much about Malthauser or the Malthauser studying. Maybe another time, so we forgot. But let me comment on some reduction results in this symplectic report action setting. So this gives us tools for generalization of momentum map theories. Classical symplectic reductions, reductions of Poisson manifolds, and so on and so on. So let me tell you that first of all, since you want to deal with the small quotients, we assume that the action on mu and is first of all 3, which means that A of G if this holds implies that G is mu of G of sorry mu of and proper which means that the map is projection to change that this map is a proper map. Okay, these are usual assumptions. So now sigma is a symplectic group weight, and then what we get is as follows. Let me change the blackboard. So first, what we get is that for each P in S, we get the quotient that's denoted by this sigma. I mean, it's denoted by this, and defined as that mu minus 1 of x divided by sigma x is has a symplectic structure, such that then you have a projection, right? So the symplectic structure pull back to the level set of mu. I mean, it's not necessarily level set, but very much. Is a symplectic form restricted to this this mu minus 1, which I mean resembles the classical Mayer-Weinstein reduction. This is of course the isotropy subgroup. Mu is then the momentum map, and this is of course the symplectic manifold by classical Mayer-Weinstein reduction. For second, but here of course it's much more general setting. I mean,
Also, coming back to your previous theorem, the second item of this theorem, like this contraction with the generator, as far as I know, in the classical Marsden-Mayer-Weinstein, you require infinitesimal generators of the actions to be Hamiltonian.
Yeah, of
Do
course.
you need this here too? Namely, do you need this contraction to be an exact one form or not?
Well, if you go with it, no, it's you don't need. I mean, if you think about the no, I don't think you don't need it.
Okay.
No, it's just no, you don't need it. You don't need it, but it's. There's another proposition which characterizes the symplectic groupoid actions, which well, maybe I will state it. I will not prove it, but I will state it. But it says that yeah, okay. Let me just
Sure.
All right. So the second is that the quotient n, which is S divided plus sigma, is a Poisson manifold, the Poisson structure, the n and the projection from S to n. Sorry, n is the Poisson. It's a Poisson. And the third thing is that in a classical symplectic setting with symplectic group actions, these are the leaves, symplectic leaves of the Poisson manifold. In this case, it will be divided by the whole equal G. So in this case, this also false, which means that the discrete leads of n are identified with connected components of S. Okay, so these are, I mean, these are the I would say classical results were written in this setting of symplectic leading points. And at the end, well, there's proposition. Let me state it quickly. Proposition. Well, just let me say one thing. Also, that this, I mean, indeed, in my opinion, this approach has its advantages, and one of them is that in this setting you can also relatively easily get the reductions. The reductions, for instance, for infinite dimensional manifolds, or much complicated things. When in the standard approach, you need to take care of many details, many technical details. But in this setting, of course, you need to also take care of all details that it's much, I would say, natural way. For instance, I mean, for Poisson homotopy groupoid, right, where it's you can, I mean, the result is that it can be presented as a symplectic quotient, but yeah, let me write this. Well, indeed, it's a classical Morrison manipulation reduction, but in this groupoid setting, it's a more natural way, I think, to do this. Sorry, but the proposition is that well, it's basically the converse of the previous propositions. Proposition which says that, well, if we have if we have a symplectic groupoid, here we need to assume connected T fibers, and as omega is also symplectic, manifold. We get that in action omega on this as M fits symplectic group reduction. If and only if it's called a momentum up condition, and it's I wrote before, just mu pullback sigma omega alpha is equal to contraction of omega. So this proposition somehow, I mean, characterize the symplectic groupoid patterns. Yeah, so thank you very much. That's all I want to say.
Thank you. Are there any questions, comments?
Yeah. Do you know? Well, thanks first of all, Bartosz. It was a very nice lecture. Do you know what happens in the presence of a Hamiltonian? Like if I have a Hamiltonian and the symplectic manifold, then you still have the you can reduce still the Hamiltonian, and then you have like the dynamics also project, etc.
Sorry, could you repeat? When you have a Hamiltonian function, you mean? I mean, you are asking about the dynamics?
Yes, exactly. Like what?
Yeah,
like
that's,
you can reduce.
Yeah, it's. I mean, of course, we can do it. But the funny thing is that in the usual, like the usual, I mean, the papers related to the reduction in a setting of groupoids, these papers do not care about the dynamics at all. And there are a lot of papers like symplectic reduction, contact reduction. No one cares about the dynamics. But yes, if you just take the paper and if you want to reduce the dynamics, the theorems holds. Yes.
Okay, I see. Thanks. Also, I wanted like to ask the question because usually when you have in the usual setting, no, having a Lie group acting on the symplectic manifold by symplectomorphisms, you usually take the momentum map and ask for it to be at equivariant, right? To do the Marsden-Weisstein reduction.
Yeah.
Here, you get at equivariance by requiring this like it is a symplectic groupoid action, or I mean, the question is whether ad equivariance is hidden, like in the definition of the action.
Well, in a special case, yes, of course. In general, it's not ad equivariant, but with respect to the conjugate action, but this ad equivariance of the momentum map is hidden in the definition of a symplectic groupoid action.
Okay, I see. Thanks.
You're welcome. So in most cases, yes, it's ad equivariance. It's already included.
Yeah.
Well, I was going to ask if you know, like, of course, all this formalism is very nice, but if you know if it has been applied to any specific example, but as you already said, like, well, when at some point there are this type of papers that just do abstract stuff for the sake of abstraction. So yeah.
Well, if you no, I don't know. I mean, no, just like the papers with this setting and applying this goes to like symplectic. Well, sorry. I mean, usually most of the papers I saw, they are just deal with the mathematical part. They do not care about the applications. In some papers, there are applications, but they are still abstract. I mean, some examples but still in an abstract. I mean, there's no physical or anything.
Yeah. Like, but do you know like any example which dealing with the classical, like, classical theorem, you get a problem and it would be like, even if it has not been explicitly done, it would be like natural setting to apply this theorem instead of the classical Lie group or Meister?
Yeah, I mean, I think I know, but I'm not sure. I mean, in the sense that I just took a look at it some time ago, and I'm not sure, but I think people in an infinite dimensional symplectic field theories. I know that there are some people. I think the paper that I'm thinking about is authored by one of the authors is a guy from Canada, and I think they use maybe even more more advanced setting using the stacks or something like. I mean, I don't remember. Maybe stacks, maybe not. I don't remember. But they apply it for field. They call them up in field theory. Yeah, I will look for this. This paper. I'll send you a book.
Well, related with, like you said at some point, that in the infinite dimensional setting, stuff become less complicated. Can you give, like, what things are complicated in infinite dimensional setting that are not so much, if you would?
Well, basically, is it recorded?
Maybe I can.
The biggest advantage of this geometric approach is that you do not need to take care of the convergence problems to discuss.
Yeah, I see. That makes sense.
In infinite dimensions, also it happens that most of the times you don't have a momentum map. There is like a. And
of course.
you need like Lie group valued momentum maps and all things that are not so straightforward. But I don't know much about that part, but maybe this fits more naturally into this Lie groupoid setting. I don't know.
Yeah, but there is also a paper of Tobias Diaz, I think, who was first to this PhD student of Ratio, and he wrote, I don't know, 2 or 3 papers about the symplectic reduction, in infinite dimensional setting, and he doesn't use this algebraic groupoid approach. He uses a different approach, more familiar with the classical one. It's a group value momentum maps, as far as I recall. And in the proofs, what he does is just very often just proving the convergence or something is very well defined. It's more like functional analysis.
I see.
No problem.
By the way, guys, regarding all this discussion about, I think we all would love to see a very concrete dynamical example, right? So I maybe have a proposal we can take a look at. It's not, of course, it is related to Lie systems, right? But it is not a Lie system, but a deformation somehow of a Lie system. And I think can put a symplectic groupoid action there. And look what happens.
Like you have a non-complete.
Yeah, non-complete.
Okay.
It is based on more specifically, it is based on a quantum deformation of SL2R. And you have there like a very, somehow a deformation of a harmonic oscillator with one particle, so 2 dimensions. And I think, there we have a Lie algebraic structure. Well, we have our Poisson manifold, and it's not difficult to look for a symplectic groupoid action there and to see what happens. And we can take a look at some point.
Okay. Perfect.
Yeah, it's
I will send you text.
Thanks. More comments or questions?
I don't think so.
Maybe we're gonna stop the recording.
Yeah. I would.